Hello, welcome back to the channel. So let's now move on to some other properties of definite integrals, and these are one of the coolest properties of definite integrals as well. So this property of definite integrals is based on even and odd functions. So let's do a recap on even and odd functions first in order to get a good idea about what these properties denote, right? So you might have heard even and odd functions in your high school courses or even in your calculus courses as well, the differential calculus courses. So if we talk about an odd function is basically, so if you have a function fx, an odd function is basically if your f of x is equal to negative of f of negative x. So if this property holds true for your function, that function is an odd function. And similarly, if you're talking about an even function, for an even function, if your fx is equal to f of minus x, that is an even function. So if one of your function satisfies this property, you can take x square as well, right? X square satisfies the even function property because if you take x square or you take negative of x square, both are the same, right? So that is why x square is a even function. And most likely you would have also heard about the two most popular even and odd functions, which are sin x and cos x. So sin x is an odd function and cos x is an even function. You can also confirm this while calculating f of x and f of minus x, and you'll clearly see that sin x follows the properties of odd functions and cos x follow the properties of even function. So this was a quick recap on what odd and even functions are. And now based on odd and even functions, we have two very important properties of definite integrals. In order to go through the properties, we'll start with assuming our a greater than 0. So a is a constant, a belongs to any real number which is greater than 0. So if your fx is an even function, this integral, if your starting point and the ending point are negations of each other, your definite integral in this case would become twice of the definite integral from 0 to your endpoint. And this property indeed will make all your calculations much easier. And similarly, if your fx is an odd function and you're doing the same thing, you're calculating a definite integral from minus a to a, the definite integral in this case would be 0. You can easily prove these properties. You can take an example of odd function and check for this property, and you can also take an example for even function and check this property. But if you want to prove both of these properties generally, you can always use the Riemann sums in order to prove these two properties. So based on these two properties, we'll do some questions in order to reinforce the idea of these properties. So we'll go over the first question, which is the integral of minus 5 to 5 x mod x dx. And whenever you'll see this case, when your starting point and ending point will be the negation of each other, you'll most likely have to use this property of even and odd functions in order to calculate your definite integral. So let's check for this function. So in this case, our function fx is x mod x, right? And now let's check for f of minus x in this case. So if I take f of minus x, it would be minus x mod of minus x, right? And mod of minus x is x because the absolute value function always gives me a positive value, and the absolute value of negative x would be x. So this would become minus x times absolute value of x, right? And now based on fx and f of minus x, we can clearly notice that f of x is equal to negative of f of minus x in this case, right? And this property is clearly a property of odd functions. And now if we use this property for odd functions, we know that whenever we are taking a definite integral of an odd function where my endpoints are the negation of each other, the integral is always 0. So that is why if we use the same property over here and calculate integral minus 5 to 5 x mod x dx by using the property of odd functions, this integral would become 0. And that would be your final answer. So this integral is equal to 0. And you can also confirm this by sketching the graph of this function, and you'll clearly notice in this case that when you'll take the signed area of x mod x from the given endpoints x equals minus 5 to x equals 5, you'll notice that you'll get a 0 at the end of your final answer. So your signed area would be 0 in this case. But how easy it was to calculate by just using the property of odd functions rather than drawing it, right? So that is why you can always use these properties in order to simplify your definite integral calculations. And now after this, let's go over one more example. So the next example we have over here is we have to calculate the definite integral of minus 2 to 2 absolute value of 2x dx. And let's check again if our function follows an odd function property or an even function property. But also notice that it would not always be the case that your function is either satisfying an odd function property or an even function property. Because if your function is not an even function, it does not mean that your function will be an odd function then. So that is why you'll always have to check for whether your function is an odd function or an even function and then use those properties. So let's check in this case. In this case, our f of x is mod of 2x. If we take f of minus x, this would become 2 times minus x. And this mod, as you know, will be changed to 2x, right? And we can clearly notice in this case that our f of x is equal to f of negative x. So that is the property of an even function. And now we can simplify this definite integral based on our even function property, right? So this integral will be simplified to twice of integral 0 to 2 mod 2x dx, right? And now we only have to calculate this in order to calculate this definite integral. And now in order to solve this, there are two ways in which you can evaluate this definite integral. You can either sketch the graph of absolute value of 2x and calculate the signed area from x equals 0 to x equals 2. But in this video, we'll use a new method in order to calculate this definite integral. So let's solve for this definite integral. We have to calculate integral 0 to 2 mod of 2x dx, right? And we know about mod x that our mod x is a piecewise function, right? It follows negative x when your x is less than 0 and it follows x when your x is greater than or equal to 0, right? And that is what we already know about mod x functions. And now if we take the absolute value of 2x, it will follow a similar thing, right? If I substitute absolute value of 2x in this case, this would become 2x, this would become 2x, and this would become 2x, right? But what's more important in this case that whenever you're taking your x to be greater than or equal to 0, you can write mod x as simply x, right? And that is what exactly we'll do in this definite integral calculation. Since our x is varying from x equals 0 to x equals 2, which means that my x is always non-negative, so I can simplify this expression and can write the absolute value of 2x as just 2x by only following the property of mod as a piecewise function. So now let's do that. So by using the property integral 0 to 2 absolute value of 2x dx would become 0 to 2 2x dx, right? And that is done only because whenever our x is greater than or equal to 0, we can write our mod x as simply x. And now we can use this thing, right? The thing which was given in the question. So we were given in the question that we can use this property that the definite integral of x dx for my x varying from a to b is b square minus a square upon 2. So let's use this property. Let's take the 2 out. So it would become 2 times 0 to 2 x dx, and this is, and the definite integral expression would be simplified to b square minus a square. Since in this case my b is 2, so b square would be 4, a is 0, a square would be 0, and this is divided by 2. And if we simplify it down, it's 4. So now we know that integral of 0 to 2 mod of 2x dx is 4. But in the original expression, we have to calculate twice of this in order to solve for this answer, right? So my final answer would be 2 times, this is 4, So the final answer would be 2 times 4, which is 8. And this is the answer to the definite integral in this case. So that's it for this video. I hope you found this video interesting, and you also might have noticed how easily we can manipulate our definite integrals in order to solve them quickly and easily. Feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye.